Okay, so we're going to be working with growth and decay. So first we're going to look at exponential growth. Occurs when a quantity increases by the same rate in each period of time. When this happens, we know that our value is going to get bigger. So here's our exponential growth function. Y equals A times the quantity 1 plus R raised to the power of T. And it says A must be a positive number. So when we were working with those graphs the other day, we said, okay, we can have A could be anything, positive or negative. Well, now when we're working with exponential growth, it must be a positive number. Y represents our final amount. A is the initial amount or original amount. R is the rate of growth as a decimal. And T is our time period. Now, most of the time periods that we work with, if it doesn't say, most of the time it's in years. Okay? And so you need to make sure you put your units down all the time too, because one thing I noticed also on that Friday homework was that we did forget units. So make sure you have this formula written down. That should be on the top of your paper, something where you can easily access it, on your note card. Okay? And we're actually going to add a minus there later on for when we do exponential decay. But for exponential growth, it's a plus. So here we have the original value of a painting is $9,000. And its value increases 7% each year. Write an exponential growth function to model this situation, then find the painting's value in 15 years. So this is asking us to do two things. It says first, write a growth function. Then find the value in 15 years. Okay? So you have to do both. Right? If you only do one, you're not going to get full credit for that. So make sure you're doing both. So first thing we need to do is identify what the values represent. Okay? We have A, R, and T. Okay. All right, do we know what A is? It says A represents our original amount. What's the original amount in this case? Okay, so we have 9,000. And R represents the rate of growth as a decimal. So,
0.7.
Okay, so it's 7%, which as a decimal, remember to move it 2 places to the left. So that's going to be 0.07. All right. And then our time in this case is going to be 15. Okay, are we going to use that when we write the function? No. Okay, we don't use the 15 when we write the function. We're going to use that for when it says then find the painting's value. So our function, y equals A times 1 plus R raised to the power of T. And then we want to simplify that. So 9,000 times 1.07 to the power of T. All right. This is our function. Okay. That's what we have to do first because it's asking us to do two things. So this is our yellow. Oops, that's green. That's not yellow. Y equals 9,000 times 1.07 to the power of T. That's my function. Now, to find what it equals in 15 years, we're just going to put in 15 for T. And then we're going to put 2 little squiggles. What do those squiggles mean? Okay, approximately. All right, this is not going to be an exact value. It's going to be an approximate. Okay, And we are talking about money, right? The value of a painting is in money. So how many decimal places do we round money to? 2 of them, all right? So what do we get in this one when we do that calculation?
24,831.28.
Okay, so this painting is now worth $24,831.28. Okay. Okay, so that's the exponential growth. Make sure you write the function and then find that value afterwards. Now, we're going to look at exponential growth in a little bit different way because sometimes it happens more than once a year. So how many of you have a bank account, have a savings account? All right, most of us have a savings account. All right. Now, if you have a savings account, then every quarter or every 3 months you get a statement from them, right? How your parents do usually.
I get a statement every month.
Okay, every month, all right? And then every month or every 3 months, they show you how much more money you got, right? They give you a dividend or something like that to reflect the interest that you've earned. Well, compound interest, when we work with a compound interest formula, it is exactly the same as an exponential growth, except it takes into account the fact that they might calculate it more than once a year. Okay? And so you'll see that there's a letter N in here now. So it's very similar, but it has this letter N here. And that letter N actually represents how many times they're going to do it each year. So the first formula that we wrote down on exponential growth, if it's once a year, that's what you use. If it happens more than once a year, then you have to put in however many times a year it happens in the place of N. And that's called compound interest formula. Okay. So example 2 says write a compound interest function to model each situation and then find the balance after the given number of years. Okay. So letter A says $1,200 invested at a rate of 2% compounded quarterly for 3 years. How often is quarterly? Okay. It happens 4 times a year, right? Hence the word quarter. You gotta like that number. Okay. So that means then when we find our numbers here, we actually need to write down that N is going to equal 4. So we're still using our other letters. Okay, we've got P, we've got R, and we're going to do N. Right? And like I said, when we write the function, T is still going to be T. Right? But we'll add that in when we go to find the other part. All right, so what's P for this problem then?
1,200.
Okay, 1,200, right? All right, we're going to start with $1,200. It says that's invested at a rate of 2% compounded quarterly. So R is 0.02. Make sure you move the decimal 2 places. And if it happens quarterly, that means we're going to do it 4 times per year. So they're using A now instead of Y. Whichever one you use is totally fine. Okay, you can flip-flop them however you want. This is 1,200 times 1 plus. Now our interest rate goes in the numerator, and how many times a year goes in the denominator. And then in the exponent we have how many times a year multiplied by how many years we do it for. So the time. So here's where you're going to want to utilize your calculator also, is that you're going to want to add this part inside the parentheses to finish your function model. So when we divide 2 divided by 4, we get 0.5, right? It's a half. So this is going to, you should have 1.005 raised to the power of 4t. Is that right? When you plug this in your calculator, you get 1.005. Okay. All right, so that is our function. Okay. Okay, we've got to have that first of all. And it says find the balance after 3 years. So we just plug in 3 for t. And my suggestion to you would be when you put that in your calculator, put it in as 12, not 4 times 3. Okay? You can simplify a lot of things just by doing that multiplication in your head. Don't let the calculator do it. You do it for the calculator. Then there's no way you can, the mistake will be made. So, Mr. Shink, what's your balance after 3 years? $1,274 and a penny. Okay. Yes, Jared. Yep. Didn't make a lot of money there, did they? Nope. 2% is not a whole lot. Well, if you ever, do you have a bank account? A savings account? Do you ever pay attention to how much more you get?
Yeah.
It's not very much, is it?
You only get 10 cents a month on it.
Yeah, it's pretty small, unfortunately. Okay. All right. Yeah, you don't get much anymore for. Yes, sir. Yeah, unfortunately nowadays they don't pay much. Okay, so find this one right here. So make sure you identify each value first. P, R, and N. So we're replacing N with 12. Okay. So then you take that and you simplify it. So I'm going to put in my calculator 1 plus 0.048 divided by 12. And you'll get 1.004. Okay, because 48 divided by 12 is 4, right? Okay. So then when we put 2 in, twelve times 2 is 24, so we're going to raise it to the 24th power. And we're still talking money. Make sure you use your dollar sign. Make sure it's there. All right. And Mr. Beebe, what'd you get? All right. You guys agree with that? Okay. Okay. So we've got exponential growth and compound interest. Both things are done the same way. The only difference with the compound interest is it may happen more than once a year. And so you have to take that into effect with our value of n, okay, for the number of times per year. All right. So let's look at decay. The rate of decay, this is exactly the same formula as exponential growth. The only difference is instead of adding the rate, we are subtracting it. So what happens is that we start at 100%, okay? And if we have growth, we're going to go over 100%. And if we have decay, then we're going to go below 100%. which means that if we have growth, our value in the parentheses there then, our value for our common ratio, okay, you can think of it that way, that number is going to be bigger than 1. And if it's decay, then that value is going to end up between 0 and 1. Okay. Now, the thing is that some people will just take that number, that 3% there, and they'll say, oh, okay, well, that just goes in there. And what happens is those numbers go down really, really fast, and they don't necessarily go as fast as we might think they do. Okay. So we're using all the same letters. The only difference is changing to a subtraction. So here we have the population of a town is decreasing, which means we have exponential decay at a rate of 3% per year. In 2000, there were 1,700 people. Write exponential decay function to model the situation, then find the population in 2012. So y equals, we're still using p, or this one they use a. All right, use those numbers, you can just switch back and forth either way. It's your starting value, however you look at it. So we have 1,700 is our starting value, and it's decreasing, so we have 1 minus 0.03 to the power of t. So then this number in the parentheses here, since it's decay, has to be less than 1. So I can think of it this way. If I take 3% away, what percent do I have left? 97. There's that 0.97. Okay? So when we're talking about decay or decreasing, we're talking about not what's gone, but what's still there. Okay? So 3%'s gone, but I have 97% that's still there, so that's my number. My growth rate then, or my decay rate then, ends up being that number there. So in 2012, how many years is that from now, from 2000? Okay, 12 years, right? All right. So in this case, we're talking about population, correct? And the population in this case is, what's our units? People. All right. So we're talking about people. So how many people do we have in the year 2012? 1,179. Okay, you guys agree with that? 0.53? Well, you can't, but we are approximating, so we're going to approximate it to those 2 decimal places. Okay? All right, and that's people. And the only time you don't do that is if they specifically say, to the nearest person or like that. But otherwise, then you should always go, and I prefer 2 decimal places. So, okay. All right. So growth, decay, very similar, just the change in adding or subtracting. Okay. All right. One more thing. Exponential decay with half-life. How many of you have ever heard of the term half-life? You did it last hour, really? Okay, all right. We did it first hour, actually, talked about half-life. So here's a formula for half-life. In first hour, when we did it, though, we used a little bit different formula, but it gives us the same thing. A, again, represents our final amount. P represents our original amount. And then we're multiplying by 0.5 raised to the power of t. It's half-life because every time period, it reduces the amount to half. Okay? All right, so hopefully your grade in this class does not follow that half-life formula, right? Every week it doesn't go down by a half. That would be rough if it did. Right, Troy? That'd be a real bummer. Okay? says acetone 218 has a half-life of 2 seconds. That's pretty fast. Okay. Find the amount left from a 500-gram sample of acetone. Now they changed it to acetone. Okay, 218 after 10 seconds. Okay. So now, here's the thing. T is a little different. T represents the number of half-lives in a given time period. Okay. So if the half-life is 2 seconds, and 10 seconds have gone by, how many half-lives is that? 5, right? Okay. If 10 seconds have gone by and it reduces by half every 2 seconds, then it's reduced by half 5 times. Okay. So this is going to be a pretty small number then, isn't it? You cut something in half 5 times, it gets pretty small. So our value for t here then has got to be 5. So we will do A equals, and we started with a 500-gram sample, and we've multiplied that by 0.5 5 times. So we cut it in half a bunch of times. Let's see, if I cut it in half once, I get 250, right? Cut it in half again, I get 125. Cut it in half again, I get 62.5, right? Half of 125. Okay. Cut it in half again, I get 31.25. And I cut it in half again, and I get 15.625. And that is grams. She's a great person when she makes me cookies. Right, Megan? Okay. All right. Okay, let's look at another one. All right, we're still talking about acetone or acetone, whichever one it is, against acetone. And okay, how much is left from that 500-gram sample after 1 minute? So if 5 times it's been cut in half after 10 seconds, how many times is it going to be cut in half after 1 minute? Okay, because a minute is 60 seconds, right? And 60 divided by 2 is 30. Okay. Oops. Let's go. All right, so A is equal to 500 times 0.5 raised to the 30th power. And I can't do that in my head. That number's getting really little. Montana, what's that number? Times 10 to the what power? -7. Okay, so really, that number is 0.00000046. Okay, grams. Grams makes cookies that size, they ain't going to be worth much. Okay?
That's not even a prompt.
No, it's not. Okay, any questions on those then? Okay, so we got exponential growth, exponential decay. When it's exponential growth or compound interest, always our number in the parentheses here, okay, it's always going to be greater than 1. Okay, so if it's growth or decay, it's bigger than 1. If it's growth or compound interest, if it's decay, then that number is going to be less than 1. Make sure you write the compound interest out first, or write down write down the function model first. Okay, they're going to ask you for the function model. You need to write that model first of all, and then find the answer that they're looking for.